Hey everybody, today we're here to talk about a spring oscillator lab. Let's head to it. So we have here is another lovely simulation from PhET, and we can see that we can have this system oscillate. Super important that when you're collecting any data for this lab that we go off to the side and we have that damping value set to none. But once we let this oscillator go, we can see that this just sort of goes and goes and goes. And in terms of the variables that we can change and the things that we can collect, we are allowed to alter the mass that we have on there through a little slider. We're also able to alter the amplitude if we were to take out our ruler. We can sort of figure out where this is and how much I'm going to pull this down. If I'm going to pull it to 20 centimeters or 30 centimeters, that's something we can pretty easily do from there. The one thing that we don't have control over numerically, at least, is the spring constant. There's a way to change the spring constant, but not numerically. It just goes from small to large, which doesn't really help us out in terms of data collection. So that two sets of data that we'll be collecting is the mass and measuring period, changing mass measuring period, and then changing amplitude measuring period. I do recommend for sure putting on the slow motion mode because that makes it a lot easier to actually measure the period. But let's dive into the graphs. So looking at our first graph that we have here of changing the amplitude and looking at the period, and wow, you gotta love these simulations with this data, right? This is the exact same value. Doesn't really matter what amplitude you pick. I just did a whole bunch of them here, and you can see this beautiful r squared of 0. And this flat line graph is telling us that there is no relationship between the two variables. A better way to say that is as we are increasing the amplitude, we are not seeing a change in how long it takes, how much time it takes for the system to oscillate. Now, this is interesting if we think about what we know about springs. If we were to stretch a spring more, there'd be more energy in that system. Right? And if I have more energy in the system, it's not changing the amount of time that it's taking it to move. I would challenge you, using your knowledge of physics, to try to figure out why this would make any sense. Why this would make any sense at all in terms of how this is okay and how this is allowed. I feel like this would be a really, really nice, fantastic justification style question for any sort of assessment that might be worked forward. Our other data set is with mass. And if we look at this data set, I did in fact add a 0, 0 on here for us, but we can see that it has that curved shape. So we're seeing that side opening shape, which means we would in fact linearize by squaring all of the period values. And if you do that, whoa, beautiful, beautiful r squared of 1, again, because of that lovely simulated data. So as always, once we have that graph, we have our linearized graph, we now want to try to pull meaning. We want to get to the point where we can have a mathematical model, obviously written there, but we want to have the mathematical model with some intent to be a little bit more general form that we can use for the future. So let's head to the whiteboard. So again, we always start with that lovely y/mx plus b format. Great, totally fine. And for this, that y value would be period, again, period capital T squared. Okay, and this would be my slope for this, would be some number, and this would be square seconds over kilograms. And then this would be mass. The intercept on this is negligible because it's so small a value, so we can just sort of ignore it. Now looking at this and sort of like trying to think about this and like what this would tell me and what this would mean, we once upon a time spoke slope for every kilogram square seconds is not something that I think makes any sense for us. But this slope actually does have a very strong meaning. Unfortunately, the app that we use doesn't allow you to pull that meaning out yourself, but I can help you out a little bit. This slope for this graph, okay, what this slope actually is, if this slope is 4 pi squared divided by the spring constant. Now, I think it should make sense that at some point the spring constant should factor in. If you have a stronger spring or a weaker spring, it should factor in at some point at least. And as we're looking at this, we can see this is where it factors in. With any and all oscillator, we're always thinking about the restoring force. What force is attempting to restore equilibrium? And in this case, it would be the spring force directly being correlated to the spring constant. Great, so let's take this and let's try to build that mathematical model for us. So we would have t squared, then we would have 4 pi squared over k multiplied by m. If we were to clean this up just a touch, we could have this as 4 pi squared m divided by k. And now, unfortunately, that's something we have talked about in the past. Not everyone loves that leading variable to have any modifiers on it. So pretty standardly, we would actually square root both sides. And if we do that, we would get that period is 2 pi radical m over k. We would call this TS because it is the period of a spring oscillator. Now, as we look at this, what this is telling me is that as the mass were to increase, more mass that's on there, it's going to increase the period. It's going to take longer for this oscillator to cycle. Okay? But with spring constant, if the spring constant were to increase, that would actually decrease how long it takes. It would take less time because a stronger spring. That should logically make sense. But it is not a direct relationship for either of those because of that square root that's there. What's interesting, if we were to look at this, is okay, that's enough. This looks really familiar to something that we just did. Something that we just worked our way through. They're not identical, but man, oh man, are they close. They are super, super close. You have a 2 pi, you have a square root with stuff in it. What's interesting is, from the experiments that we did, the lab we did, notice how the numerator is the primary thing that we were able to modify easily that affected it. And in the denominator, that's the thing that correlates to the restoring force, where little g correlating to Fg equals m times little g, and k correlating to Fs equals kx, or Hooke's law. Very interesting. The 2 pi there, 2 pi. How many pizzas I want? How much pie there is at a family gathering? More like too many pies. Or how many radians there are in a circle. Yeah, that 2 pi is there because there's a cyclic nature to all this. There's a cyclic nature, the fact that these things are repeating their cycle over and over and over again. Interesting. So great, with these two equations, we are now powered up to work our way through any and all of the oscillation questions that we have remaining. Hope you found this video helpful. I'll see you in the next one.